Academy of Water Resources, who will be co-sharing this session. So this session today has been jointly organized by Asian Disaster Preparedness Center, ADPC, and Vietnam Academy of Water Resources, VAWR, through one of our ongoing flagship program. It's a regional program called SERVIR-Mekong, which is a joint initiative of United States Agency for International Development and National Aeronautics and Space Administration, NASA, with the aim of harnessing space technology and open data to help address development challenges related to climate change. So with our partner organization, Vietnam Academy of Water Resources, we have been working jointly over the years through this program, basically to improve the drought monitoring and forecasting capabilities of Vietnam, and with the aim to further improve the operational planning and decision-making process in the country. So through our session today, even though this session has originated through this joint collaboration between Vietnam Academy of Water Resources and Asian Disaster Preparedness Center, but today's session will basically make you familiarize with some of the ongoing works in the Asia-Pacific region as well as in other countries around the world, mostly related to water and disasters. And I hope this session will provide better insight into these ongoing works and also give an opportunity between the presenters and the audience to have a close interaction in the field of water and disasters. So once again, I thank you all and I welcome you to the session. But for today's session, just give a brief insight. We have 3 oral presentations and we have 1 poster presentation. So the oral presentation, the first one is on pre-processing of radar-based rainfall estimation for real-time flood forecasting and early warning system. This is from Mr. Narongrit Loandilo from Hydro Informatic Institute in Thailand. The second presenter will be Miss Rufaya. So she is from the Irrigation and Hydraulics Engineering, Tanta University, and her topic is on climate change impacts on precipitation patterns over Egypt. And the third is on advances in short and medium term riverine flood forecasting over the Lower Mekong Basin. So this will be a presentation from Mr. Miguel Leverde Barajas. So he is one of the researchers from SERVIR-Mekong. Apart from that, we do have a poster presentation, as I mentioned earlier. So this is on the use of remote sensing and GIS for drought risk assessment, the case of Southern Province in Zambia. So this will be from the University of Zambia's Integrated Water Resources Management. So these are the 3 oral presentations and 1 poster session that we have for this particular session. Now, with regards to the session timing, so let me give you a brief overview about the session, the timings of the session. So each presenters will be given 10 minutes to present, and then it will be followed by question and answers after each of the presentations. In the interest of time, we request that the audience can put your questions in the chat box, and after the presentation, we will forward these questions to the presenters so that they can give the responses to the audience. So with this, may I now invite Mr. Nangrongrit from Hydro Informatic Institute to deliver his presentation on pre-processing of radar-based rainfall estimation for real-time flood forecasting and early warning system. The floor is yours, Mr. Narongrit.
Thank you. Let me share my screen. Can you see my screen? Okay.
Yes, we can see it. Yeah.
Okay. Good morning and good afternoon. I'm Naronglit, model developer from Hydroinformatics Institute, Thailand. And today, what I would like to show you is the pre-processing of radar-based rainfall estimation for real-time flood forecasting and early warning system. And when we talk about model or forecasting system, the data is very important. So in this study, we will demonstrate how to basically test radar rainfall data and also show something that need to be considered. It is well known that rainfall takes an important role in flood forecast for the urban area like Bangkok, and flood may occur within just in the 15 minutes. And sometimes you can see that density of rain gauges over the area could not be sufficient for capture all of the rainfall event. And at this time, weather radar is very useful too for estimate the rainfall amount because of it provide high resolution in spatial and temporal. And also another one is radar image can be projected to a near future by using the image processing technique. And to make use of the radar, background knowledge and some data pre-processing is needed. And in this study, the objective is to understand the characteristic and limitation of the data and try to identify error and uncertainty from radar data and try to eliminate them. And in this study, the data from Nong Chok radar is used in this study, and it is a C-band dropper radar with a 5.6 gigahertz and 120 kilometers of maximum range. It's located in the eastern part of Bangkok. And I have to say that this study used collected reflectivity from that collected by radar manufacturer. As you can see that I'm just a modeler. I'm not a radar expert, so I use some product from the radar. And to reach the objective of this study, we follow this step. The first one is check the obstacle in the radar, such as terrain and building, and try to identify the sector or the location which are affected by beam blockage or ground cluster by statistical analysis. And also, we also compare the rainfall amount with the ground truth, which is rain gauges from our institutes. First of all, the radar scan from different elevation angles are plotted in order to check the data quality, and you can see that there are a lot of cluster in the first elevation angle. So in this study, we select the second elevation for further study, and we can estimate the height of radar sample and check with the terrain and building height to make sure that our radar is not potentially affected by anything from the ground. To identify the error in the radar, we also can also consider the probability of detection or POD with the certain threshold in a different period. You can see in the figure on the top. And there are two notable error features in the POD map, and it including the beam blockage and some electromagnetic interference. Beam blockage feature can be seen in the lower quadrant, in the lower left, in the lower right quadrant, sorry, and which is POD value is quite lower than those surrounding sector that are not blocked by anything. And we can see some electromagnetic interference appear some and randomly in the red dot line, which is the POD value in the sector is a bit higher than those surrounding sector. And this kind of issue always occur in the C-band radar, which located nearby the city center. And fortunately, there is no strong source of interference in our area. So in our radar, we can remove it by just filter it out because it is just the lower value of the reflectivity. We can ignore it, and it maybe give us we cannot detect the very light rain, but our system will focus on the heavy rain. It should be fine. And finally, we also select some rainfall event from rainy season, and rainfall amount can be estimated by general CR relationship and compare with the rainfall from rain gauges. And you can see in the figure in the right hand side. As you can see the lower figure, we also show ratio between rain gauge and radar, and it plot into it plot with the distance from the center of radar, which is the positive value. It means radar underestimate, and negative value mean it give an overestimate rainfall. And the radar, in our case, our radar tend to underestimate along with increasing of distance from the radar center. And this is what we expect to see. And it is important to make a note that the radar have their own effective range. And for someone who would like to use the radar-based rainfall in the system, they must make sure that their target area is in the effective range. And summary, the error in the radar can be identified by data statistics. And the results show that there are different error exits in our North radar, which is beam pocket that come from the building or man-made structure, and some interference from maybe from the unlicensed instrument, which emit the signal in the same range of the frequency of the radar. And to apply radar-based rainfall in the system, in some system or any system, the effective range should be considered. And there still be a room for improvement. That is, we may apply more complicated algorithm to eliminate the dynamic error, such as the interference from the other instrument on. And another one will be we calibrate CR relationship and maybe apply some machine learning based rainfall estimation into the system. And one thing that we didn't do that is try to apply rainfall from the rain gauge to make an adjustment in the real time. That is what we have to do in the future. Thank you.
Thank you, Mr. Narangrit. Anyone has any questions from the audience side, please feel free to drop your question in the chat box. I don't see any questions. So is there any questions from okay, there is one question. So range 125 kilometers. Did you do the calibration with shorter range?
Range. Yes, but yes, we can. But I think we should consider the whole area to make it to give the overall performance. It depends on your focus area, I think. We can calibrate it with the different length from the radar if you have enough data.
So just a quick question from my side. So is this work currently piloted work, or it is already a kind of work which has been implemented in a larger scale?
In other scale, right? Now we just only focus on the in the Bangkok area and
okay. Okay, then I don't see any other questions from the audience side. So thank you once again for your presentation. And now we move to the next presenter, Miss Rufaida from Tran University. So her topic is on climate change impacts on precipitation patterns over Egypt. So the floor is yours, Ms. Rufaida.
Okay. Good morning. Hello, everybody. Screen is
Hi, can I be able to screen? See the screen? We see us now at the moment, so that's your presentation. Slide 2. Now we're back to... when you share your screen, you cannot see us anymore. You only see your presentation. When you show your presentation, you cannot see us. So just show your presentation and talk.
okay. Good morning. Hello, everybody. Our presentation is entitled Climate Change Impacts on Precipitation Patterns over Egypt. Outlines of our presentation: introduction, objectives, data, methodology, results, conclusions, and recommendations. During the last century, climate change is a serious hydrologic threat because increasing in temperature driven by greenhouse gases, and it leads to change in precipitation patterns as shown in the figure. Some regions have upward trend, experienced upward trends, and other regions have experienced downward trend, and also found that there is a change in rainfall intensity where there were areas experienced severe droughts and the other extreme flash flood events. Regarding our country, Egypt has a semi-arid climate. The rainy season extends from October to March, and rainfall occurs in December, January, and February. Annual rainfall ranges between 200 mm in the north coast of the country and almost nil in the south of the country. Annual quantity of rainfall equal 1.3 billion cubic meter. From this, 0.4 billion cubic meter are used in supplement in irrigation of the Nile Delta, and rainfed agriculture exists along the Egyptian north coast. In the last decade, Egypt has experienced a dramatic flash flood event which has increased significantly and noticed through this figure the locations of flash floods. This table shows the number of victims and the economic losses. For example, 2025, the flash flood results in 5 persons were killed. The main objectives of this study to study the effect of climate change or rainfall characteristics in Egypt to investigate spatial and temporal changes in precipitation characteristics over Egypt and to assess spatial and temporal variations of the projected annual precipitations under different climate scenarios. Our data, we collected the precipitation series from 31 gauge stations scattered throughout Egypt as shown in the map from National Climatic Data Center. For the projection, we used the project simulation model to represent climate change over study area according previous studies. The results of this simulation are available in the Cortex website. 10 indices calculated for data in 3 categories: annual, seasonal, monthly. Annual contains annual maximum precipitation, annual total precipitation, annual number of rainy days, and simply daily intensity index. Seasonal maximum precipitation, seasonal total precipitation, and seasonal number of rainy days. Monthly maximum precipitation, monthly total precipitation, and monthly number of rainy days. The study methodology divided in the two main stages. The first one for trend analysis. Before applied trend analysis, we applied data quality assessment, Durbin-Watson test to detect serial correlation for precipitation series, and 3 absolute homogeneity test, von Neumann ratio test, standard normal homogeneity test, and Boutet test, and then applied trend tests for 2 categories: parametric test, Robertson R test, and non-parametric test, Mann-Kendall and Spearman with thin slope magnitude. To assess the similarity between parametric and non-parametric test classification was proposed as 3 categories as shown in the table: extremely likely, likely, less likely. The extremely likely refers to detected trends in both parametric and non-parametric test, but at least one test must be at 5% significant level. For likely refers to detected trend of 10% significant level or was detected to use one test at 5 significant levels. The less likely trend refers to detect at one test or less at 10% significant level. For the second, for precipitation projection, we used observed data from 1995 to 2014 at 15 stations across Egypt. 3 widely used bias correction methods techniques have been applied to rainfall data bias correction method, linear scaling, local intensity scaling, and empirical quantile learning. The bias correction precipitation are compared with observation period 1995 to 25 using frequency-based indices and time series-based matrices. This study projected rainfall in Egypt in the context of climate change for 3 future periods under 3 different scenarios. The results achieved the first objective: temporal trends. All stations are homogeneous and independent. For all indices, 63 detected significant trend, 15 detected upward trend, and 48 detected downward trend. For the precipitation projection bias, we use bias correction method as shown in the figure. Raw data and observed data by applying 3 bias correction method: linear scaling, local intensity, and empirical quantile measuring. All methods are able to improve the precipitation quantity derived from RCM time series, but there are substantial difference in their ability to reproduce precipitation data that have characteristics comparable to that observed data. For comparing with bias correction method, we use the cumulative distribution function of the observed raw bias corrected precipitation for 3 methods. RCM simulated has a highly underestimated rainfall with all probabilities. After applying the 3 bias correction methods, we found the empirical quantile mapping was matched with observed data, so the empirical quantile mapping performed the best method, and then applied frequency-based indices from 6 categories: mean, median, standard deviation, coefficient of variance, 99 percentile, and the probability of wet days. From the figure, we shown that the linear scaling was the worst method, and empirical quantile mapping, local intensity mapping is the best like for most of stations empirical quantile mapping, which relates the observed data to the empirical quantile mapping with the best method. Secondly, time series based matrices show 6 categories: root mean square error, mean absolute error, percent of bias, index of agreement, mesh efficiency, normalized root mean square error. From this figure, we show the empirical quantile mapping is the best method in the most of index. Further, based on the results, we use the empirical quantile mapping to project the annual precipitation. Firstly, for the annual maximum precipitation, the projected rainfall varies greatly depending on the scenarios applied. In the future period, overall, most of stations are expected increase significant in increase in rainfall changes. The western part of the country is the most affected by the climate change, anticipating a significant increase for 3 scenarios during 3 future periods. In contrast, the regions Nile Valley, Delta, and North Coast experience decrease changes. For RCB 8.5, nationwide, the rate of increase in annual maximum precipitation is expected to decline by the end of the century. Secondly, annual total precipitation. The results of annual total precipitation, like annual maximum precipitation, most of stations expected increasing trend, and the western part has highly affected with changes in rainfall pattern. Third, annual number of rainy days. We used the most of stations has experienced increasing trend throughout the country, and under RCA 8.8 nationwide, the rate of increase in annual number of rainy days is expected to decline through the end of the century. For single daily of intensity index, most of stations increasing changes in rainfall pattern. Some parts increases showed decreased changes in south and central of the country, and the most affected in the western part and the Sinai region of the country. Our conclusions: the rainfall series at 31 stations were quality assessed, prevailing dependency and homogeneity. Most of the detected trends were negative, indicating a decrease in the precipitation amount, rainy days, and intensity. The deduced trends don't form any systematic spatial pattern. Decreasing trends were detected in northern and western parts, and the increasing trends were detected in the central and south of the country. The rainfall simulations were extracted from the most reliable RCM. Its output were adjusted by applying 3 bias correction methods, whose scales were ranked using different matrices. The most appropriate method, empirical quantile mapping, was adopted to project the annual precipitation indices under 3 RCP scenarios during 3 future periods. Egypt would experience a formidable increase in annual rainfall quantity accompanied by a significant increase in the number of rainy days. The maximum increase was observed in the western part. In the meanwhile, the rainfall was predicted to decrease over some scattered districts throughout the country. The alteration in rainfall differs significantly according to the applied scenarios and future periods. The design of hydraulic works and infrastructure should be adopted to consider these likely changes in rainfall characteristics during their whole lifespan. The expected increase in precipitations over some regions in the western desert and Sinai could be vital to expand rainwater harvesting projects to recharge the groundwater aquifers and increase rainfed agriculture lands. Our recommendation to locate more meteorological stations with the recent common period of record in order to determine the possible climate change signature in rainfall data in Egypt. Additional studies on the expected correlation between hydrological and climatic variable will be available. To consider possible change point or the possibility of long-term persistence. To study extreme rainfall estimations in the context of non-stationarity. To form a multimodal ensemble using down-scaled RCM outputs to increase the reliability and credibility of the data projections over Egypt. Our publications. Thank you for attention.
Yeah, thank you very much, Miss Rufaida. So any questions from the audience? So I don't see any questions from the audience. Anybody from the panels, co-chair, or any one of you, the presenters, have any questions for Ms. Rufaya? Okay, so I have a very what do you call? I have one particular question, basically related to the projected information that you have shown. So, which suggests that in the long run there is a possibility of decline in rainfall in some of those uh, areas in Egypt. So, what is your long-term approach? Do you think that you should adopt in order to overcome those kind of a situation?
I can't hear. Sorry, I can't hear the question.
Oh, okay. Can you hear me now?
Yes.
Okay, so my question was, I could see that there is a projected, decline in rainfall in the near future and in the mid future and the far future situations. So under that conditions, what would be, have you also looked into what would be your future strategic approach to minimize the impact? Basically, when you look into the agricultural sector, do you have any recommendations, or do you have any kind of preparedness plans or something that you are thinking based on the outcomes that you have achieved?
So اللي هو using rainwater harvesting for agriculture lands and to use rainwater harvesting.
All right, that's fine. Yeah. Okay, thank you, Ms. Rufaya. Then if I don't see any further questions from the participants as well, now I move to the last oral presentation, that is on advances in short and middle term riverine flood forecasting over Lower Mekong Basin, implementation of new bias-corrected near real-time and forecast rainfall information into Mekong River Commission flood early warning system. So this presentation will be given by Mr. Miguel Levardi Barajas. So the floor is yours, Miguel. Miguel, you are muted.
You mute.
Sorry, now. Can you hear me now?
Yes, go ahead.
Okay, thank you so much, Richie. Sorry again. For introduction, my name is Miguel Laverde. I'm Geospatial Data Science at SERVIR-Mekong program. And on behalf of the person described below, I will introduce to you the title is Advances in Short and Middle Term Riverine Flood Forecasting over the Lower Mekong Basin. So, to give a context about the area, like to the one that are not familiar with the Mekong Basin, normally this area is highly dynamic, like the Mekong, the Lower Mekong Basin. As you can see in the picture, this area has double threats. In the east, the Indian monsoon summer, and from the west, the East Asian summer monsoon seasons threat several trigger floods and flash flood events over the whole area. So, in addition, this is one interesting publications presented last year in Nature, where the area of the east, the area of the east, like is the Indian summer monsoon, was evaluated, and then was evaluated in 2100, predicting that countries like Thailand or Myanmar could expect a maximum increase around 20 millimeters per day. These kind of conditions make particular prone the Mekong Basin to flood events. So the regional organization is the Mekong River Commission, which corresponds to intergovernmental organizations composed by the countries of Cambodia, Laos, Thailand, and Vietnam, are mandated to provide management the shared water resources in the Mekong Basin. For that reason, they developed a system called the MRC, Flood Early Warning System. It's a modular hydrological and hydraulic models developed under the FUSE platform created by the Tares to provide riverine for forecasting for short and medium term. During the dry season, the system provides information weekly basis, and during the flood season, which corresponds to the months from May, latest May to October, provided information a daily basis. For short-term predictions, the system uses the near real-time data. This is used Trinh and SRE. This is from NOAA, provides information at 25 kilometers every 3 hours. And for medium terms, the system uses the rainfall forecast, the GFS, to this information provides information up to 6-day forecast at 25 kilometers information, at 25 kilometers spatial resolution. So one of the issues for this kind of systems comes from the data itself. There are several uncertainties in rainfall data coming from the natural variation of the rainfall data, and also the errors that the satellite data contains. For example, it's been studied that the satellite data contains errors coming from the topography, for example, the type of rainfall, and the sensors that the satellite is composed. Also, in case of rainfall forecast, there are several uncertainties. For example, numerical weather forecast contains several errors to predict rainfall in tropical and near tropical regions dominated by a large mesoscale convective system, such as the Mekong Basin. So the objective of this project is under the SERVIR-Mekong program. It's a joint collaboration between USAID and NASA, and then is to support a better riverine and flash flood forecasting system for the Lower Mekong region. The objectives is divided into components. First, to improve the accuracy of near real-time based rainfall for short-term prediction. And the second objective is to incorporate the state-of-the-art past-corrected SERVIR-FS to improve the medium-term riverine forecast. So the methodology is divided into phases. In the screens, you can see the current status of the system, of the MRC FUSE system, where all the inputs in near real-time and rainfall forecast are included into the system to provide early floods, early alerts. In the first phase, the objective is to include the latest GPN emerge early version, which has a resolution of 10 kilometers every hour, and to incorporate a operational tool for bus correct GPN operational basis. It's called GPN Vehicle. For the second phase, the project aims to incorporate this is the SERVIR-GFS. This is the bus correction rainfall forecast. This information is this database contains information at 5 kilometers resolution, with the 5 kilometer resolutions up to 15 days rainfall, 15 days ahead. This bus correction database have several versions. The latest versions provide information up to 15 days, daily updated. So every day you can have 15 days ahead. So For this evaluation, we use the previous version, that the previous version has a latency of 5 days, 10 days forecast ahead, but also the system, which is incorporated, provides information at 15 days rainfall forecast. So the tool, the operational tool, is called GPM-BICO for short-term riverine forecast. This system is a open source tool. This is a Python-based tool designed to correct GPM immerse using multiple bus correction methods. The system is adjusted to incorporate this, to tailor the information provided by MRC for daily basis, and then works operationally on daily basis. And also provided some basic evaluation to evaluate the performance. For example, this one is included the root mean square error, the correlation coefficient and bias, currently like the system. This is the interface of the system. Normally, like, the users can just include the chef file with the location of the in situ data that they want to correct, and the Excel file with the rain measurements. So the users can select for different approaches: uniform distribution, spatial bus correction, and spatial temporal bus correction. And lately, we incorporate the gamma quantile mapping. This is in the latest version to bus correct. Also, the system is available in GitHub. This is the direction. This is the address that you can find this tool. It's open source that you can download. The methodology for the medium-term riverine forecast is the SERVIR-VFS. This is a bias corrected and downscale version of the NCEP, Global Ensemble Forecast System. As I mentioned, they have the information at daily, 5 days, 10 days, and 15 days rainfall forecast at 5 kilometer resolution. This is how normally this is the data. If you can see that this is the original data, and then how the system is bias corrected and downscaled. This is this product was made by the Climate Hazard Center from University of Santa Barbara. So in SERVIR-Mekong, we have this product in our tool, Service Decision Supports tool, Climate Serve. This tool provides information. Users can download information through a user interface. You can see, for example, in Climate Serve, that serviglobal.net, you can go through and see, you can extract this information. And for operational basis, also, we add a Python-based tool. It's called GetChefGFS to automatically download ChefGFS at daily basis. One characteristic of this tool is this information is quite heavy. So in countries like for example, like countries like Cambodia, they have difficulties to download this information. So with this one, we are testing like this we can use in low connections, low internet connections. You can download it. So, okay, the result for this information, we evaluated for short terms. We evaluated during the monsoon period from 2014 to 2018. We use 129 stations for correction, and then we use 138 independent stations for validate the performance. This is the performance. Blue label corresponds to the non-corrected, and the light blue, yellow, and red represents the different bus correction schemes that the satellite rainfall data is corrected. So you can see that different methods perform, like the methods were able to correct, to reduce the root mean square error and the bus correction and the bias. Also, in our analysis, we we were able to provide that 25% of the room square error and bias was reduced considerable. And also we evaluated the hydrological response for in case of stream flow prediction. We use a simple conceptual hydrological model located in the upstream area. We use the head HMS to evaluate the performance at different levels, and then we see that the performance also, like the correction of the past of the rainfall data, improves the stream flow prediction. In case of medium term for rainfall forecast, we evaluated during 3 monsoon periods, 2017, from 2017 to 2019. We evaluated from 1 to 6 days to match the information from the previous data, and 1 to 10 days. And then we use GPM bus corrected as a reference data. So those are the results comparing the previous data, the GFS, compared to the CHIRPs. In this graph, we see that the GFS provides a lower room mean square error and a highest correlation. And also we evaluated some indexes, some categorical index, to see how the both products performs. And then in this one, we see that the GFS provided the highest detections, probability of detections, and almost the same false alarms. And in overall, the performance is higher in GFS. So those both tools were already, we are working with the center, with the Mekong River Commission Center, to incorporate the system into the Fuse platform. Here you can see some training that we have last year, and also here you can see how the system, the bus correction, is included into the Fuse platform, and also some preliminary results that we have in case of GFS. In this graph, you can see that with the previous rainfall satellite GFS, you can have lower station, lower. You can predict lower, and with the height, you can predict during the longer periods. So future lines that we are working on right now. Also, this is one example that we have is we are incorporated the tool GFS tool at national level. That this is some result that this is one organization in Vietnam called National Center of Water Resources Planning and Investigation, NAWAPI. They're using the GFS tool in their prediction, in the water allocation forecast prediction, and this is some daily bulletin that they deliver to the country. So, in summary, the SERVIR-Mekong supports MRC in access the latest information for near real time and rainfall forecasts. With the GPM BICO tool, we were able to reduce considerable the bias and the room mean square error for the IMERS data, and also the hydrological models also suggest that we are increasing the accuracy of the rainfall data. We are able to improve the flood prediction. In terms of GFS, we are able to increase the period for the forecast from 6 days using the previous version to 15 days, also with higher resolution. And also in comparison with the GFS, with the previous system, GFS has the lowest temporal and spatial resolution for longer forecast during monsoon seasons. And the latest one is also this is also to encourage MRC to implement this GPM BICO and GFS into the flood forecast system. Just to finalize, also those tools, all tools that we are presenting right now, are free available in this link in GitHub SERVIR-Mekong. Also, you can see not just for rainfall, also you can see for flash flood detection, for flood inundation. Sorry, you can go through through this link, and then you can download this, the tools. So, like this. Thank you so much. This is the contact that you can contact any members of the team. Okay. Thank you so much.
Thank you, Miguel. And I could see one question from VAWR from Dr. Trinh. So his question is, hydrological and hydraulic model, is it coupling and using the existing model at MRC?
Yes, thank you, Dr. Trinh, for your question. Yes, the system, the characteristics of this platform is the system is coupling first run the hydrological model and automatically run the hydraulic. The hydraulic that they use is 1D, and this one I saw that is what in this part is they use another system is similar to SWAT, is semi-distributed, but they're using coupling, yes, in the system, inside of the view system.
Yeah, any other questions from anyone? Okay, so there is another question from Dr. Trinh. Can you comment about the application in smaller basin, the case study with NAWAPI, whether it is comparable to the Mekong Basin case study? So basically the comparison between a big and a small area.
For the extraction, they're using just the data to extract information. That might be difficult to compare based on both, like the purpose of both systems are for different, have different aimings. So, but if they are already included a system running operationally, that will be, yes, that there is something that can be done. But if this specific case, that will be different that will be difficult to compare.
Okay, so there is another question from that's coming from Vietnam. Actually, it came. So this question is, do you think this model and the method could be applied in other regions out of Mekong region?
The system right now, like the tools that we are describing, are developed for the Lower Mekong Basin. Actually, that's why we are tailored the information for that to get advances to, because the problem with this kind of tool is we are automatically download the global data, and then in areas, for example, Cambodia, they have a very low internet connection, and then we need to download the data to be able to use in such environments. So the tool like this is just for the Mekong, but however the algorithms and everything, yes, you can apply everywhere.
Okay, so thank you so much, and I think I don't see any further questions from the audience. Ms. Quien's question has already been answered. Thank you, Miguel. And with this, I think we have come to the conclusion of the oral presentations. And now I would hand over the session to our co-chair, Dr. Tran, to give his remarks on the session before we close the session for the day. Dr. Tran.
Is that the poster presentation is going to be included also?
Already included. So, is he going to present it, or how he is going to?
I don't know. Is that like he's going to be present because that I think that like he's on the agenda. So, Michael, are you prepared, or you talk a little bit about the poster? Because I think that it's good.
Yeah, I think that would be great. Yeah.
Yeah.
So, Mr. Mikkel, are you going to give a brief overview about your poster?
Yes, I can. Yes.
Okay, please go ahead.
Can you see my screen share?
Yes, we can see it. So you can make it full screen, then it's fine.
Oh, but I already have. I don't know why it hasn't changed there. Can I go ahead?
Yeah, please go ahead. Yes.
Okay, so I'll give a poster pitch on a study we did at the University of Zambia. It's titled "The Use of Remote Sensing and GIS for Drought Risk Assessment." So this was done in the case of the Southern Province, which is the southmost province in Zambia, in sub-Saharan Africa, Southern Africa. So we particularly went for this province because it's one of the food baskets of the country, but it seems to be hit by droughts on a more consistently than most other provinces in the country. To add to that, there is very little infrastructure for resilience to droughts in the province. And on top of that, there are very few meteorological stations for people to collect information. So we opted to use remote sensing to sort of assess the droughts in the province. So there were 3 objectives. The first one was to determine the drought hazard itself using different indices. The second one was to investigate if there were some correlations between these indices and appropriate physical parameters such as rainfall. The third one was to identify and outline the drought hotspots in the southern province using the drought hazard exposure and vulnerability. You can see the methodology, I hope. So the method we use data in our methods. We use the MODIS NDVI. This was monthly. We also use the CHEPS precipitation. That's from 2016. We got actual precipitation data and soil moisture data from the meteorological department here. Maize yield and production data from our statistical office, and population and poverty data from the statistical office as well.
Just to interrupt here, Mikkel, it seems your presentation is not moving.
It's not moving?
Yeah.
Oh, okay. It's moving here. I don't know. Okay.
Hi, Michael. It's Marina here from Congress again. Maybe just stop screen sharing. No, don't stop screen. You said you put it on full screen, so just stop full screen for yourself, so you see the slides yourself in the editing mode. That should solve the problem, I think.
Oh, okay.
All right.
You can see the slide, the methods one.
I myself see 2 slides at the moment.
Yeah, I can see 2 slides. Yes.
It's one on top of the other. I don't know what's going on.
All right. Shall we maybe just start screen sharing again so you can go on? That would be my suggestion. Just stop screen sharing and share again.
All right. Okay.
All right. And this time, don't go on full screen. Just go ahead like it is now. And then you should see, then it should work. All right.
All right, thank you. So yes, I was saying the data we used was the MODIS NDVI, the CHEPS rainfall, monthly precipitation and soil moisture from the meteorological department, maize yield and production from our statistical office. We also got some poverty data for vulnerability. For the drought hazard, for the meteorological drought hazard, we used the rainfall anomaly percentage and the SPI, the standardized precipitation index. For the agricultural drought hazard, we did the normalized difference vegetation index and the vegetation condition index, which is a derivative of the NDVI. And we also use the SMI, the soil moisture index, which is also NDVI based with the inclusion of land surface temperature. So the correlation analysis was dependent on whether the data is normally distributed or not normally distributed. So when it's normally distributed, we did the Pearson's product moment coefficient for the parametric test. And when it wasn't, we used both the Kendall-Tau and the Spearman's rank correlation. So for the drought risk assessments, the risk itself was a function of hazard, exposure, and vulnerability. We used the weighted overlay to combine the three elements, and the exposure was determined using populations and land cover, and vulnerability was determined, as I mentioned earlier, by poverty headcount, slope, and rainfall variability. Okay, so has the slide changed? So for the results, I have 3 maps here. These were done by district because usually assessments for droughts here are done by district. So we aggregated them to districts. But some of the more interesting results we had is that the droughts were a bit different when they were caused by an El Nino event, in that they were regressive in nature. That is to mean they started off really intensive, and then they sort of reduced as the rain season went on. And then from our SPI, we expect that we would have an extremely dry drought every 18.3 years. And we also realized that the province itself experienced more dry years than wet years, which was similar to some other findings as well in the area. And then because El Nino itself is typified by higher surface temperatures in the country, when we're doing the triangle method for the soil moisture index, we realized it wasn't a triangle per se, it was more of a trapezoid shape. So this would be used as some kind of an indicator to tell if we're gonna have a possible drought. And then the highest correlations that we found were within the grasslands, and that was with NDVI and rainfall. And then also the vegetation condition index and the SMI were also significantly correlated to the respective parameters. So our conclusions with looking at objective 1, as mentioned earlier, we had 2 kinds of droughts that we saw. When there was an El Nino event, we would have a drought that was more regressive in nature, in that it became less intense as the season went on. And when there was the absence of El Nino, we noticed the drought would become more intensive as the rain season went on. Well, extremely and severely dry events occurred more frequently. That was during this time period, there were 13 extreme results, and then only 6 extremely wet results. The trends of VCI were similar to that of maize production and yield. And then the onsets of droughts were characterized by higher land surface temperatures. As regards to objective 2, NDVI was significantly correlated, which was to be expected, but it was more correlated in the grasslands and the croplands, which was useful for agriculture. And significant correlations, that's about 0.2 between soil moisture and SMI, was only at a 5 centimeter depth. So at other depths, beginning from 10 centimeters going up, there was no significant correlation. So for the last objective, the meteorological drought hazard was highest in the part of a district called Kazangola. This is particularly interesting because it lies in an area that's expected to be less hazardous. And then this CHTM ward in Kalongo district was the most vulnerable in the whole province. And then the southern parts of Kanzagula were high risk. So was Kalomo, Sinazongo, and Zimba. And thank you.
Thank you, Mr. Mikkel. So I can take a couple of questions, even though we are running out of time. Does anybody has any question for Mr. Mikkel? Okay, so I think there are no questions from the audience. And thank you very much for your presentation. And now, before we conclude, I would request our co-chair, Dr. Trinh, to give his remarks.
Okay, thanks Rishi, and thanks to all presenters. I see that a lot of results of the remote sensing and geospatial tool has been used, whether it's going to be the flood risk of floods, early warnings, or like for the drought. Because like we see a lot of that in Vietnam as well, and that is also along the line with the cooperation that we have with the SERVIR-Mekong programs, and I see a lot of like a similarity with all of the presentations. What is happening in Vietnam? I see a lot of potential as well regarding the use of geospatial tool, remote sensing data for supporting the decision-making process. The main conclusion or like main taking point away is that like we need to improve the accuracies of those data or like those generated information from remote sensing, so that like we can be able to better inform the decision making as well as the communities for their water related management. The same issues in Vietnam, so that like I think that the communities or like also the research community also need to improve our tools, and then also kind of like the interface with the community, so make them be aware about that, like how the tool can be able to use to support their decision or their management practices. And we this is the last remark from mine, is that like we are also very much fortunate to have the cooperation with SERVIR-Mekong and ADPC, so we improve a lot of our capacity as well over here using the geospatial tool and the other tool for water related management. So I think that like for our session today, I think if Rishi have one other comment on for our session, so I would like to thank all of you for the participation, and please enjoy the other session and also the wrap-up session of our conference today.
Yes, thank you very much. So with this, we conclude this session, and please enjoy the other sessions and see you next time. Have a nice day.